Let's start. Welcome everyone. My name is not Klaus Peters, my name is Johan Elnert, and unfortunately Klaus Peters, he missed his flight this morning. So I'm jumping in, and I hope you excuse if there are some improvisations or mistakes, but anyway, I'm the managing director for the forest-based sector technology platform. So I deal with wood as raw material, which might be interesting to complement the speakers here. About the speakers, I will come to that soon, but first maybe it's good to know that you have this Slido function, and I've been told that if you go into this website and you choose room B, then you can post questions, and you can also like each other's questions, which put them on top. And if that's correct, and then we can actually ask those questions in the end of the session. So this session is very much about the title is very long: Industrial Symbiosis, Secondary Material Resources, Resource Recycling Technologies. But a lead to what we'll talk about is more under the annotations or the questions. For instance, can innovation help securing sustainable supply of raw materials to the EU industry? And how can circular economy contribute? That is a very open question that I think we can bite into. So we have here 4 very eminent speakers. One of them has, just like me, been called in in the latest moment. So also we thank you very much for that, Samir. First out to present this topic is now Mr. Koen Koppenhole. And Mr. Koppenhole, he's the Chief Executive for Semburo, which is the European Cement Association. But before that, he was also the head of European affairs for a little company called ArcelorMittal in Brussels. And Koen also has a magnificent career in law. He has also graduated magna cum laude from the Leuven University of Law. So actually, I think you have an old colleague or study friend from Leuven here. And you also hold a degree from Harvard Law School. So you will talk about the cement industry in the circular economy, if I get it like that. So please, welcome to the podium. And meanwhile, to all of you, please don't forget to post question on this REinEU question forum. Thank you very much.
Thank you. Good afternoon. Can I try one? Yeah, is this okay? Yeah. Yes. Okay. Now you can hear me. Okay. Is this better? Just let me know when it's going down again. I will try to shout from here, but let me know. Good afternoon, everybody. Indeed, I would like to say a few words about the place of the cement industry in the circular economy. And it's true that if you look at the title of the presentation, it's all about industrial symbiosis, using materials from other industries to make sure that we are part of that circular economy. I mean, yesterday I was in a meeting in Brussels with the European Commission, and there the idea was that the cross-industrial efforts are increasing, and that basically we're no longer looking at silos when we look at industry, but we look more and more at integration of several industries, and I think that is certainly true when we talk about the circular economy. Before I start my presentation specifically, let me say a few words about Semburo, what the association is about and what we are doing. Semburo has 29 members, 27 full members and 2 associate members. We cover the whole of the European Union. Unfortunately, Slovakia is not part of our membership and Malta is not part of our membership. The rest is. We have a cooperation agreement with Cyprus, and we have 3 non-European countries, of which Turkey, which is a very important cement producer worldwide. So we have Turkey, Norway and Switzerland as non-European members. Our main activities consist in conveying the messages from the cement industry to the European institutions, which includes, of course, also the national governments. Let me then go into the details as far as the circular economy package is concerned, and I will basically state the obvious in this slide. It's something that you're all familiar with, but I do want to repeat it and to set a little bit the regulatory framework in which we operate. You know that the Commission is now going through a revision of its Waste Framework Directive. There is a waste to energy communication that will be published by the Commission, and we will have now the date for January 2017. The key elements of the Commission's package is that there is a common target for recycling of 65% of municipal waste by 2030, a binding target to reduce landfill, and a harmonized calculation methods for recycling rates throughout the EU. Another important point is that there is an extended producer responsibility to make sure that you use your waste in a responsible way that is relevant if you're talking about industrial symbiosis and use of waste across several industries. So that is the setting, that is the regulatory framework in which we operate. Just a word about the cement sector. You can't see it very clearly on this slide, but I will just explain that if you talk about cement, the cement sector is always compared to the steel sector, to the wood sector. Now, if you're talking about steel and wood, you're talking about the product that you see and buy on the market. Cement basically has one additional step to get to the markets, and in most cases, it's getting to concrete. We build our houses concrete, our infrastructure with concrete, and basically the step before cement is clinker. So we have our raw material, which is limestone. Limestone is decarbonated with a 70% process emissions included. The rest is fuel emissions. We make clinker, and then from clinker they take the last step to cement. And then basically we add water and aggregates to come to concrete. Concrete is actually a low carbon product which basically has about 10 to 15% of cement only. So please make that distinction between cement and concrete. Concrete then contributes to sustainable construction, to houses of today and tomorrow, and to infrastructure needs that are prevalent across the world. So that's a little bit the background of us. What we're talking about today is mainly the clinker production process. As I said before, production of clinker is the part of the cement manufacturing process that is most CO2 intensive, most energy intensive. And that's basically what we're talking about today when we're talking about alternative fuel use. We call it co-processing. What does it mean? It means that when you are manufacturing clinker in the cement manufacturing process, you basically use normally primary fuels, which is petcoke, oil, which is indeed also responsible in terms of fuels for a lot of CO2 emissions. We try to replace these primary fuels with what we call alternative fuels and alternative raw materials. Now, how do we do that? Co-processing in the cement industry, and that's an important point that I want to mention here, and it is already recognized in guidelines of the European Commission. We're talking about a combination of energy recovery and material recycling. So you see the difference I make between the recovery, energy recovery, recycling of materials, and that will be important for the rest of my presentation. But we always emphasize that the co-processing in the cement sector means that we use waste from other industries, and we use this waste for both energy recovery and material recycling. This clarifies it a little bit on this slide. when you look at alternative raw materials, you can have construction products, for instance, that are used. You have all demolition and construction waste from buildings. Part of the aggregates can be used in the cement sector again. We can use sands, we can use slag from the steel sector, we can use ashes, and we can basically recycle the material in these products to replace some of our primary raw materials. The same is true for our alternative fuels. We have paints, we have plastics. You will see that on the next slide when we go a little bit in detail. But the alternative fuels can replace the primary fuels, petcoke, oil, as I discussed before. Part of that is also a material recycling of some of the products. So you basically have both material recycling and energy recovery in the cement kiln, which basically means that you do reduce your recourse to primary raw materials. So there is the energy efficiency and the resource efficiency more specifically. And you use, in order to do that, you use products and energy from other sectors and other industries. And that's where the industrial symbiosis comes in. That's where the circular economy comes in. When you look at the breakdown that we have in the cement sector, on the left side of the slide, you see that we still use around 59% of fossil fuels, so that's the primary fuels that we still use. But we have indeed alternative fossil fuels for 36.7% and biomass for 4.3%. So we come at about 41% use of alternative fuels in the cement sector. If you look at the vision and the way in which we use the alternative fuels, and that is then going further into the red part and the green part, you have different sources that we use. We use tires, we use solvents, we use animal waste, we use sewage sludge, impregnated wood dust, all these elements we use from other industries in our industry. I mean, just for your information, when we're talking about biomass, it's about waste biomass. I mean, you're talking about animal bone, animal meal that we use in our processes. That is what we call the energy recovery. Remember, I was saying that the cement industry does both energy recovery, material recycling. So here we're talking about energy recovery. When I'm talking about material recycling, you basically see that in 2014, we used a total of 145 million tons of raw materials, 5 million tons alternative raw materials, and then ashes basically for 2 million tons. So we have a substitution rate for the raw materials of about 4.6%. So raw materials on the one hand, energy recovery on the other hand. The footnote on that slide is also important because some people might say, yes, but what is then the relationship between the cement industry and the normal incinerators? It's true that we always say there is a market for both, but in fact the cement industry has for a long time not been recognized and acknowledged as one of the potential intake sources for waste. And that's basically what we want to put forward. When you talk in Europe about building additional incineration capacity, we are saying, well, before you decide that, look a little bit at the potential that is there for the cement sector, in the cement sector, because we need these waste streams in order to make sure that we comply with our environmental requirements and with the obligation to reduce our CO2 emissions. I go to a few examples. I mean, this is the refuse derived fuel or solid recovered fuel in a municipal waste. That is a fuel that is produced when you shred the municipal solid waste. There is 12 million tons of that type of waste. And again, as I said before, 5 million tons used by the cement plants. There is 7 million tons used by the incinerators. So waste to energy plants also use that type of waste. That has a 20% more or less material content which is recycled into the clinker. I think the important point there is to say that when we use material recycling, that material that we recycle completely goes into the end product. So we don't have any losses during the process. It is incorporated into the new product. That's where we basically talk about recycling of the product. Another example that may be closer to your daily activities and world is that we also have end-of-life tires. Around 92% of the end-of-life tiles are sent to recovery for co-processing in cement plants. That is actually one of the examples that is clearest in terms of the combination of energy recovery and material recycling. Tires have a high calorific value, which means that you can recover the energy from the tires, and you have also some of the material content, more specifically iron and silica, that we need in the cement manufacturing process, which is recycled in the clinker. So we have both recovery of energy and material recycling. We have emphasized this dual nature and the dual capacity of co-processing very much because we know that member states in the European Union have an obligation to achieve recycling targets. And what we are saying is that the material recycling part in the cement sector should be able to count towards the recycling targets of the member states. I mean, that is the discussion we currently have, also with the European Commission and with the member states, is to say, how can the material recycling in the cement sector be recognized in the recycling targets at national level? That's a discussion we have. You see two examples here on how we can boost the recycling targets. What does it mean for us? As I said before, the material recycling means that we save primary raw materials. So on an annual basis, we save about 7 million tons of raw materials. When you talk about energy recovery, we save about 6.5 million tons of coal, and we reduce our CO2 emissions by about 16 million tons per year. So I think that is where our contribution is to the CO2 reduction and to the less use of primary fuels. If I have to end, and that was also a request for this presentation, what are now, when I'm looking at all this, what are now the policy recommendations that we would have? The first one I already addressed. It's basically acknowledge that the cement sector is there, that there is capacity available to take in waste from different waste streams. So that is something where we say we have 160 cement kilns across Europe, so make sure that this is used for the recycling and the recovery. What we also advocate for is a landfill ban for recoverable and recyclable waste. It's clear that that is something that is on the agenda of the European Commission. It's not always that easy to implement it at national level, but I think landfill ban is clearly high on our agenda because, again, we need access to raw materials, we need access to waste as part of our raw materials. And then the last point is the point that I just highlighted, is to make sure that the minerals that are recycled throughout the co-processing or co-incineration, they should count towards the national recycling targets. That's a point in the discussion on the revision of the Waste Framework Directive and in the upcoming communication on waste to energy. So all this to say that we have a place in the circular economy, we have a place in the discussion on waste to energy, and there I would just like to end my presentation. Thank you very much.
So thank you, Cohen, a lot for a very good presentation and overview. And when waste becomes such an important input, it's also difficult again to define waste after all. So thank you very much. And now we also remind you if you can post questions. We start to have some questions in the Slido app. But now I would like to move on to present the next speaker, who is also named Johan. But Johan Televen, who is a full professor and head of the Leuven Laboratory on Molecular Cell Biology. And you're also director of the Department for Molecular Biology. And you're the Chief Scientific Officer for Global Yeast, which is a startup company, I think. And you are going to tell us about this company and also about the transition from petroleum-based economy to a sustainable bio-based economy. So actually, you and I, we might have some similar ideas for our sectors. And please now, we will be very interested in hearing your presentation. Thank you.
So I would like to thank the organizers, first of all, for the kind invitation to give this presentation today, which will be concerned with the sustainable production of biofuels and bio-based chemicals with microbial cell factories. So the transition from a petroleum-based economy to a bio-based economy is one of the greatest challenges, actually, of our times. To produce biofuels and bio-based chemicals with biomaterials, either sugar or biomass, we need microbial so-called cell factories, microorganisms that can convert with high productivity and high titer the sugary materials into biofuels or bio-based chemicals. When we look at first generation bioethanol production, which is actually very active nowadays, we see huge bioethanol production in the United States using corn. In Europe, corn and wheat, but also sugar beets, for instance, are used for bioethanol production. In Brazil, sugarcane, juice, and molasses. Molasses is a residue from the sugar production. Most ethanol plants in Brazil produce both ethanol and sugar. Is used for bioethanol production on a very large scale. And then in quite some other countries, actually, molasses, the residue of the sugar production, is also used for first-generation bioethanol production. Other materials include cassava, for instance. There are quite some other foodstuffs, actually, food materials that are used for bioethanol production. But it would be much better if we could use so-called second-generation substrates for bioethanol production. Either waste streams such as forest residues in northern areas, corn cob and corn stover, recycled paper, wheat straw, bagasse. Bagasse is the woody residue from sugarcane, which is available in huge quantities in Brazil. Empty fruit bunches from palm oil cultivation, for instance. But then also bioenergy crops. These are crops that are especially cultivated for biofuel production, but is not really yet in commercial scale these days. And as you can see here, the hydrolysis that comes from this type of waste stream materials or woody materials is very dirty. I mean, it's very difficult material for yeast to convert the sugar into ethanol. But also the pre-treatment of the material is very cumbersome. The enzyme cost is very high. The yeast has to ferment xylose, which is a sugar that it normally cannot ferment. It's an artificial property that you have to confer on the yeast. And also these hydrolysates contain multiple inhibitors that are very toxic for the yeast cells. So in the FP7 NEMO project, we have been able to construct the first industrial yeast strain that had a high xylose fermentation capacity and also a very high inhibitor tolerance. And that actually could convert both glucose sugar and xylose sugar in lithocellulose hydrolysis with a great productivity, high productivity into ethanol. Nowadays, there are several of these so-called cellulosic yeast strains available. And actually, we have now moved from the demonstration stage into the industrial stage, commercial stage, where we have about 6 large-scale commercial bioethanol plants using second-generation substrates. The first one was built in Italy, in Crescentino. Then there are 3 plants that have been built in the United States, so Dakota, Kansas, and Iowa. And there are 2 plants in Brazil that work with bagasse, both of them. These plants are not so large as the first-generation plants, but still they have capacities of about 100 million liters of ethanol per year, which is about 50%, let's say, of a first-generation ethanol plant. So with respect to current developments, two striking developments that we have seen happening nowadays is that the plants like to, the industry likes to combine the first generation with the second generation bioethanol production. For instance, in Brazil, sugarcane is used in most plants to produce both sugar and ethanol. The sugar production also results in molasses, is the residue of the sugar production. And bagasse is the woody material that remains from the sugar cane. So the bagasse is generally burned to produce electricity, but there's a large surplus of bagasse. So the bagasse is used for second generation bioethanol production, but as I told you, the lignocellulose hydrolysis have very high levels of inhibitors, which makes it difficult to obtain a certain titer, the required titer of ethanol, and the required productivity. That's actually why nowadays the plants mix molasses together with the bagasse. Molasses also has high inhibitor levels, but the inhibitors are different from those in the lignocellulose hydrolysis. So when you mix the two, you actually dilute the inhibitors from the two substrates. And this gives rise to very profitable ethanol production, like the one in Piracicaba of REinEU is the most profitable second generation bioethanol production nowadays. A similar development we have seen happening in the United States with a so-called 1.5 generation bioethanol production, in which the corn grains are not only used to make ethanol from the starch, which is the classical first generation process, but the fibrils, which is about 40–50% of a corn grain, the fibrils, which is lignocellulose material, are converted into ethanol with a cellulosic yeast strain. And this gives rise to, say, 1.5 generations, again, a mixture of first and second generation bioethanol production. And obviously, this is quite profitable for the plants because, for instance, the distillation of the ethanol, which is quite expensive, can be used for the two processes, first and second generation. But all these plants suffer from children or baby problems. I mean, one of them is maybe rather unexpected, is the pre-treatment of the biomass. With a steam explosion, for instance, not only explodes the lignocellulose material, but apparently also the equipment. It's highly corrosive, damaging to the equipment, so new pre-treatment methodologies have to be developed in order to make this really feasible at a commercial scale. The enzyme cost. The enzymes are used to hydrolyze the lignocellulose polymers into free sugars that the yeast can use, convert into ethanol. And the enzyme cost is still about 20% of the ethanol cost, which is, of course, high. The inhibitor toxicity is still an issue and reduces the productivity of the yeast fermentation and thus also the productivity of the whole ethanol plant. What is quite striking is that the artificial property that we have engineered into the yeast of being able to convert xylose into ethanol, that this artificial property is most sensitive to the inhibitors and the stressful conditions in the plants and in the process. So the productivity needs also further improvement. With respect to bio-based chemicals, I mean, these chemicals are nowadays produced from sugar, also by cell factory microorganisms that have been engineered to produce these chemicals in high titers and in high quantities. One of the easiest ones is lactic acid. Lactic acid is already produced by yeast, engineered yeast, rather than ethanol. The yeast produces lactic acid and is already more than 10–15 years old on commercial scale. And the lactic acid is used to make bioplastic, biodegradable plastic. Also, succinic acid has been realized, I mean, with yeast also, commercial production in large quantities of the succinic acid, which can also be polymerized into biodegradable plastic. Another alcohol, isobutanol, is a longer alcohol than ethanol, has a higher energy content, can be used to make jet biofuel, and also can be used as a platform chemical to make many other variable chemicals for the chemical industry. This field of producing bio-based chemicals with cell factory microorganisms is actually booming. I mean, both in the academic research and in industry, there's a lot of work, a lot of developments are ongoing because everybody sees that there's a huge potential in this industry. But the challenges are also great. I mean, lactic acid was quite easy. Succinic acid is not so difficult. Isobutanol is already a little bit more difficult. But the novel products that companies want to make, I mean, they require highly challenging metabolic engineering. I mean, and the metabolic pathways, the control, the regulation of many metabolic pathways is not well understood, which makes it difficult to make cell factory organisms with high productivity and realizing a high titer, the required product titer. Many products that the companies want to make are actually toxic for the microorganism. This is also true for ethanol. Ethanol is also toxic to yeast, but lactic acid, succinic acid, isobutanol is very toxic. And the toxicity of these products is an issue, is a big problem in this self-factory production. Another issue is the stress tolerance of the microorganism. As I have said, these microorganisms require a lot of metabolic engineering, which makes them weak. Okay? These artificial self-factory organisms are much weaker than the natural microorganisms that come from nature into the system. That means that there's a lot of problems with bacterial contamination in the non-sterile large-scale production, because you cannot make biofuels or bio-based chemicals in large quantities in sterile conditions. And so to counter bacterial contamination, the use of low pH is one of the best strategies. But then when you want to produce acids like lactic acid, succinic acid, they are much more toxic at low pH, which creates a new problem. Another challenge is the use of the GMO microorganisms. When it's in contained use, I mean, it's generally not a problem for the product, but the disposal of the microorganism, either as animal feed in quite a number of countries, is an issue, and the discharge into the environment, even as compost, is an issue. As for the bioethanol, it would be very nice if we could produce bio-based chemicals using biomass rather than pure sugar. But this is even more difficult, and especially the downstream processing, the isolation and purification of the bio-based chemicals from these lignocellulose hydrolysates is a very challenging task. Suggestions for the policymakers. What we definitely need is more research, more basic research on these self-factory microorganisms. How the metabolic pathways are regulated. I mean, we know the pathways, but how they are controlled, how they are regulated, this is something where we have too little knowledge. Improvement of stress tolerance in these microorganisms is really crucial. I will give an example here of what we would like to do actually is to transfer stress tolerance traits from one species to another species. And it's quite striking if you look at the yeast species, for instance. We all know Saccharomyces cerevisiae is the yeast that produces ethanol. But there are many other yeast species, closely related yeast species. Clavomyces marxianus has a very high thermotolerance, much higher than Saccharomyces cerevisiae. Zygosaccharomyces bailey has a very high acetic acid tolerance, much higher than Saccharomyces cerevisiae. And acetic acid is one of the main toxic inhibitors in the lignocellulose hydrolysates. Zygosaccharomyces zucchi has a much higher osmotolerance. So if we could transfer, if we could find out why these closely related species actually have this type of very interesting, attractive traits, and transfer them to the Saccharomyces cerevisiae yeast to make the ethanol, that would actually be very, very interesting. Another suggestion is that we need more support for the transfer of the lab scale results to the pilot scale conditions. Another important issue is the GMO situation. It's really time now that the EC provides a clear and unambiguous definition of GMOs in the legislation, and that they use a robust and science-based attitude towards the use of GMOs in the industrial biotechnology. Another suggestion that is very much in discussion is the elimination of the so-called cisgenic microorganisms or cisgenic organisms from the GMO regulations. It has already been done actually in Argentina. Cisgenic organisms are genetically modified organisms with naturally occurring alleles, so naturally occurring mutant forms of genes. So the same species. So it's actually accelerated breeding. While transgenic GMOs, transgenic organisms, are genetically modified with genes from other species, which you cannot obtain by breeding. So there is a very big discussion nowadays to limit GMOs to really the transgenic organisms and exclude the cisgenic organisms from the GMO legislation. Would be an enormous progress. What I think that we also need is more support for the development by the industry of flexible large-scale production facilities in the industrial biotechnology, rather than the key-on-the-door facilities that we have now. Similar to the pilot-scale service companies, which are much more flexible in the use of multiple substrates, generation of multiple products, and flexible production process and production and process conditions. And then finally, my personal commitment in this story is that indeed I'm a professor at the University of Leuven and department director of the VIB, but I'm also the scientific founder of a startup company. Global Yeast is a Brazilian-Belgian startup company financed by Brazilian and Belgian VC funds with a headquarters in Rio de Janeiro for business development and with very good connections to the Brazilian bioethanol industry. And the research and development site is actually in my laboratory now, but we will move next year to the bioincubator. And the mission of the company is to develop superior industrial yeast strains for the production of bioethanol with first and second generation substrates and the production also of bio-based chemicals. We have in total now 14 people in the company. And finally, I'd like to thank you for your attention.
Thank you very much, Johan. And also it's interesting to see that you have one leg in a very fast-moving research field and another one in a industry that is depending on bulk and high investment costs, and where you have to maybe, I don't know, have 20 years of repayment before you have a successful manufacturing. So when do you take on board the new technology, so to speak, and build a new factory? So when do we have the circular economy? Okay, next speaker now. I would like to present Mr. or Dr. Witold Kawalek, who is a mathematician and mining engineer, and lecturer and research worker in the Faculty of Geoengineering, Mining and Geology at the Wrocław University of Science and Technology in Poland. And your main fields of interest is mathematical modeling of systems for mining industry, and also you write something here that I never heard before. I heard about fuzzy logic, but here you write that you like to use fuzzy numbers. So let's see if we see any fuzzy numbers in your presentation. Okay, but please.
Thank you. Mr. Chairman, ladies and gentlemen. Yes, how it work? Oh, good. I would like to. Oh. I am taking you to the more energy-consuming industry, the mining industry. And the introduction must contain some explanations. Indeed, European raw materials industry have tough challenges. There is a need for reducing energy consumption. There is a need for more climate protection and more sustainable activity. However, there are many examples that moving some industry from Europe outside means less sustainability, more energy consumption, and the industry is rather more dirty than in Europe. So perhaps there is a responsible solution and approach to make most of what we can do within Europe to retain also heavy industry and to be able to supply the European Union with own raw materials instead of being dependent on imported ones only. So these are challenges. KGHM Polska Miedź, a giant copper producer in Europe, supplies copper to the world market, but obviously operates in the world competition, so it must control and reduce consumption of energy, and it must look on sustainability. There are challenges, and they are tackled by the company. Therefore, the company and our university and the research office joined the Horizon 2020 research and innovation project Desire, which is focused on embedding the more information system, also closed process analyzer technology, into raw materials processing. I am telling about the impact onto the non-ferrous metal processing. there are collaboration within the project which helps to find solutions, and some already got achievements, and further steps should be useful and productive for the KGHM if they decide to implement solutions that are expected to be achieved. Just short look on the company. You can see the worldwide activities of KGHM, but the domestic or home activity is in southwestern Poland. You can see the active mining fields, prospective mining fields, and the fields that are in exploration stage. So, large company. Some key facts. You can read several numbers that prove that it is really big company, but number of staff, really deep mines, difficult geology, means that mining there is difficult, and also processing of the ore is difficult. What is very important, this is a giant energy consumer. 2.6 terawatt hours per annum means up to 2% of the total electric energy consumption of Poland. So it is a giant energy consumer. Any reduction of this means little, means not little, means a lot of energy saved. Some few words about the mining technology, because probably you are not aware of this. You can see a map of mining developments, belt conveyors, large lines of belt conveyors that transport copper ore. The copper is blasted, then transported by cars, by trucks, to belt conveyors, then to the shafts up and processed. And as you can see, the ore is delivered in big lumps. Those lumps have to be crushed, then milled. Here you can see fine particles that are flotated. However, these three processes depend on the ore that is supplied to the processing plant, and various types of ore required a little bit different activities, a little bit different settings of those machines. It would be better for the processing plant to look exactly what ore is being supplied to them. However, as you can see, it is not easy, because the general lithology of ore contains dolomites, shale, and sandstone, changes from one mining field to another, and those digital blocks shows the differences. And this material, even known in the mining field, being loaded on conveyor belt, is then mixed or blended with another material, loaded, and finally there is a mixture difficult to be distinguished. And this is the input of the DESIRE project, as mentioned before. Why not to add information to the raw material stream in such a way that this stream can say something about itself? If we put small tags or sensors onto the stream, on the place where the ore is loaded, then after transport, those tags can be read, information from them recalculated, and we should know something more. The technology is provided by the DESIRE partners to KGHM, the special tags, the readers, and obviously it can work only if we have sufficient information communication technology environment, and there is in KGHM, there is a digital ore body model, mine plan, which provide information about the consecutive mine advances, mine model, which numbers and identifies places from where the ore is being mined, belt conveyor control, which gives the information about work of running of conveyors, and this information, while taken together and processed, should provide the ore processing control with more accurate data about the ore being delivered there. The workflow of proposed and being developed desired process analyzer technology solution, from preparation the pellets on sensors, annotating them, then after transport reading and processing the information to get the results. Again, the input, the valuable input of Desire partners is processing of big data. Cloud computing is used for this. Sorry, can you run this? Here you can see the simulation model of flow of material. The small X which arrives on the conveyor belt represents the tag or the sensor which was put into the loading point and then transported with the ore up to the shaft. Here you can see how the bulk material behaves in bunker of ore bunkers that are, for instance, here. So you can see that blending is not very easy. At those simulation models I used for supplying the assessment. So this was about getting the knowledge of the material, but the large belt conveyor system also consumes a lot of energy, and the energy can also be saved. There are some SCADA systems already implemented in KGHM, a lot of sensors that get information from machinery equipment, and if this information is taken, the signals, the diagnostic signals, taken, smoothed and read properly, they provide information about fault, which can cause a breakdown. After repair, the diagnostic signal goes back to the proper stage. Here you can see the signals from good, bad and repaired machinery. And all this leads us to condition-based versus the previous resource-driven maintenance, decreasing breakdowns time, decreasing idle work of conveyors, which obviously means only wasting energy. Another solution to the belt conveyor system is replacement of energy-consuming elements like belt and idlers with the more efficient ones. Oh, sorry, I don't know why it is red. This is old solution, modernized and funny. And this is the output. So you can see this is the comparison of resistance to motion. It means consumed energy. Tests made in situ in the underground mine in very tough conditions, which are really difficult to operate. What we can get from all those impacts? The impacts should get us energy saved and more sustainability production. Assume we can recognize the ore being delivered to the processing plant better, then using the results of real measurements, you see that the energy that is necessary for grinding specific mixture of ore can vary. The energy can vary for up to 40%. The specialists from processing plants declare that even 1%, this is very conservative estimation, of improvement might give some 0.35 million ton of euro used for energy, only for grinding. Next impact. maybe even more important, not only we can save energy, but also while supplying the processing plant with recognized ore, and while better tuning of processing of ore beneficiation processes like grinding, milling, and also flotation, we can increase metal recovery. So it means we can get more from the natural resources. Also very conservative estimation tells that even increasing the recovery from 90 to 90.1% gives more than 2 million euro in value of metal earned by KGHM, but means also tons of copper supplied to the industry instead to be poured on the tailing pond. Large belt conveyors transportation system can also save energy by avoiding idle time, what was taught, and also by the replacement of standard into more energy efficient equipment. Just looking at one branch of a single mine, if we replace the old belts and idlers with the new ones, we can save, taking into account the output and the average number of hours, we can save so big amount of energy and money spent for the energy. This is for this transportation branch only, and for the whole KGHM, here are potential savings. This project is being run now. What is at the moment being done, cloud-based big data processing of data stream. In situ experiments are being prepared and soon start. A comprehensive workflow procedure that takes information from several already existing systems and added some new ones to provide the information of the copper ore. And the algorithms for efficiency estimation, fault detection are under development, but some of them have been developed, checked against standard policy, and proved to be successful. Closing remarks. These presented results that were achieved and are expected have been possible due to a Desire project, which helped the non-ferrous industry in Poland to be supplied with some solutions already developed in Sweden, as you can see below, Italy and Israel. And the specialists work together. There is a strong cooperation between the partners in the project. The project should be finished with proposals tested in the industrial conditions. Obviously, next steps depend on the company, but there is visible successful solution for the company to reduce energy consumption and increase metal recovery. Thank you.
Thank you very much, Dr. Kaulec, for showing us that also a circular economy needs a steady and stable feed of raw material in. So we are gradually, I think, we are covering different raw materials, and we're coming close to the question session in the end. So please don't forget to post your questions. So now I will take the opportunity to present our last speaker, which is Dr. Samir Bojabur from Tata Steel. And you are working with as a knowledge group leader for industrial and construction applications. So if you want to add a few words on top of that, Samir, please feel free to do so.
Okay. Thank you, Mr. Chairman. Ladies and gentlemen, good afternoon. Yeah, I will say one or two things about myself, but first let me make it clear I am not Dr. Klaus Peters. I'm only 50%, and the other 50% is the chairman, because his role today was supposed to be both. Yeah, unfortunately, his flight was cancelled this morning, and he asked me last minute to step in on the assumption that we are both from the same dinosaur. So I said yes, and although my background is not in process, it's more in application. So, but I will do my best and present his slides. So on that front, so you have to bear with me, and I'll do my best. Yes, yeah, my name is Samir Bujaber. I'm from Tata Steel Research and Development, based in the UK. I run the construction activities within, well, the R&D construction activities, looking at various things, but mainly focusing on steel applications. So you can see that the process is not my my area. Okay. Starting with the brief introduction to ESTEP, which stands for European Steel Technology Platform. And Dr. Peters, he's the Secretary General. I chair one of the working groups within the platform, the construction platform. It's been up and running for almost 10 years, and reconfirmed recently in 2013. It's been influential in launching some significant projects, in this case the ULCOS, which is relevant to this topic. We've got 66 organizations and more than 200 people involved in the platform. We develop a strategic research agenda, which we communicate with the stakeholders, but also with the European Commission, which we use as a roadmap for further work. And the role of the platform as well is not just doing the work, but also making sure it's implemented and followed up. And of course, it's an open invitation to all to join. Okay, back to the topic, the industrial symbiosis. I mean, the basic definition is, as we understand it, it's basically an association between two facilities or two companies or two industries, where the waste or the byproduct from one could be of use to another one. This concept is very well known within the steel industry. It gives us a number of opportunities. Basically, we recycle most of the process, and we'll see in the follow-on slides. As we can see on this loop, basically we start with the raw material. It goes all the way through to becoming a product. Then few loops around that product, and then it goes back to as an input scrap into the process. For example, if you can see some figures, in 2015, out of the 166 million tons of steel, more than half that, more than 50%, is basically scrap. So you can see the significance or the amount of recycled steel that goes back into the chain. Of course, we work closely with the other sectors like construction, automotive, and packaging, where also the recycling content is very high. In auto is 100%. In construction is even more. Is more than 90% of the steel gets recycled. So it's. I mean, the loop is well established, but we're still working on that, how we can make more use of the scrap and not just taking it back into the chain. As we can see in this figure, you can see the steel industry is at the heart of other industries. Basically, all the we feed all the byproducts to other industries. Could be water treatment, construction, as we've seen earlier, the cement, and it's very well linked. It depends on the industries. Some you can get only one byproduct. Others you might get combination, maybe two or even three. So the key point there, it's well linked with the other industries. That's on a high level. On a specific examples, for example, we can see the granular slag feeds into the cement, then becoming an infrastructure, in this case a bridge or a building or whatever. Same as the basic oxygen slags, leading into fertilizers, and sometimes we can't imagine that this can be possible. And the same for dust. So a number of byproducts lead or feed into other industries. One example here is, I have clicked twice on this. Sorry, there was supposed to be an animation, but I'll explain what it is. This is, for example, a specific or one example of the steel, the steel production, the steel processes. And the pie chart, basically, we can see that more than 70% is a byproduct that goes into other sectors and it's sold. It's a sales. Just over 20% goes back into the steel making processes, and a small chunk of this, about 6%, goes into landfill. This is one particular business of one particular steel maker in Europe. It's not the steel industry, just one example. And the reason for the 6%, it's not technical. It can be recycled, just it's not a cost-effective way of doing it at this moment in time. If we look at the previous example was one steel producer in Europe. If we look at the overall picture in Europe, not per producer, roughly 26 million ton is through the blast furnace, and the rest is through other means like the electric arc or the basic oxygen furnace. The point here, we can see that the blast furnace route, it's 100% recycled, while on the other route there is a tiny bit, which is less than 10%, that goes into a landfill. That's at the European level. And again, as I mentioned earlier, it's not a technical challenge. It's not yet a cost-effective way of doing it. But you can see the difference between the two methods. The blast furnace is 100%. Okay, so far we've seen an overview of how the steel industry is well embedded into other sectors and the rate of recycling. However, I mean, you can say it's the loop is well established, but the journey for us is not there. We're still getting on with some work. What can we do with the recycling? I've got 3 projects to mention. One of them is the TASU project, and it's a SPIRE project. So we're looking at other ways. I mean, this one is basically developing a waste heat recovery system. So what can we do? It's not just leading into fertilizers or slag. So what else can we do? In this case, it's a waste heat recovery system. And as I mentioned, it's a SPIRE project. It's about 18 months or so. It's got another couple of years to run, and there are 8 partners involved in this project. Another project is it's in Germany by ThyssenKrupp. It's a national program, and this one is looking at the carbon capture and what can be done with the recovery. And it's leading to a couple of ways: the fertilizers, but also energy usage. Another project, it's quite a large one. It's Horizon 2020. It's more than 100 million euros investment. It's led by ArcelorMittal, and it's about the carbon capture and what we can do with it. And again, it's leading to fertilizers and energy. The point here is those two technologies we've just seen, they are not just specific for the steel, they can also be used in other industries, like the chemical, transport, food, or the cement industry. The point here is, although we're focusing on a couple of outputs like the fuel and fertilizers, there is no reason why we cannot explore other outputs. It's only the focus and the remit of this project. But then once we get the technology, we can explore other possibilities, but also the technology can be transferred to other sectors. Okay, coming to the regulations. Of course, I mean, this area is well regulated, and there are legislations for this purpose, for the byproduct. The key message here from the steel sector, it's we should not underestimate the effort that has been put in to get to the point where we are in terms of almost closing the loop. And what we would like to see, although there are a number of legislations and there are still yet to come, we're looking for to carry on with this successful story and some supportive and non-contradicting regulatory framework. So really what we would like to see is a framework that will enable and help this effort and make it more a success, but also transfer it to other sectors. And we should not really underestimate all the work that has been done so far. Okay, just to summarize, as I said, this concept is well established within the steel sector. We've got the loop closed with a very, very tiny bit that goes into landfill, and that's, as I said, it's not for technical reasons, but it's more cost effectiveness. The 70%, more than 70, in fact, at this moment, it's about 72%. It's our byproducts, they get used by other industries, and we feed to a number of them. It's like a web, and we are somewhere in the middle. We play a key role in there. And we're looking more for legislations that will keep this good and successful story going, and more and helping it to establish itself across Europe rather than just one sector. I believe, yeah, okay. Thank you. Thank you.
Okay, thank you very much, Samir. And now actually steel and all that almost made me thirsty hearing about it. It's also like a modern drink. Anyway, time flies when one has fun. We have covered a lot of different raw materials and circular streams, but I feel I need to complement the picture a little bit with the circular bioeconomy and the forest-based sector. Because after all, in Europe, we are harvesting and using about 400 million cubic meters of wood each year. So this is about half a ton per European citizen or EU citizen. And this wood is then used for everything from chairs to biofuels and to construction materials and paper. And the EU actually has a world record in recycling when it comes to paper. Recycled paper is the most common recycled product, and the recycle frequency is over 70%, and that's close to the theoretical maximum. So on the paper side, the circular economy is already there, so to speak. On the other part of our sector, more on the solid wood or construction material, then the recycling frequency is almost zero. So that's a shame, and there is a lot to do still. So that is not to forget. And also speaking about the how much raw material we have, one should know that there were more wood harvested in 2007, before the financial crisis, than it is today. And there are no prognosis that we will harvest more wood in the future. So sometimes I think in Europe we have focused very much on the lack of raw material on all aspects, and not so much on what we actually can do. So with that little note, let's now try to come to the questions that you so patiently have provided us with. So I have a blinking. So we have one very popular question, which is to Mr. Koppenholle here. It's on the new processes are emerging to cure concrete with CO2, thus capturing it. Is this an interesting way to recycle CO2?
Yes, actually, I'm happy about the question, because it gives me opportunity to also say that indeed, as I said before, concrete low carbon product because little CO2. Now, if you look at concrete in use, and that's what we're talking about, how can we indeed recarbonate concrete? And that's basically, or what is the recarbonation process in concrete? Concrete during its life cycle interacts with air, and basically therefore there is a CO2 uptake in the concrete. So CO2 can get absorbed during that process. That is the recarbonation process that we are currently investigating. There is research going on, but that is indeed one of the ways in which CO2 and recarbonation can take place. That's a first development. Research is ongoing, but that is also the reason why at European level we are pleading in favor of a life cycle assessment of buildings. You need to look at concrete not in its application and coming out from the cement manufacturing, but also in its application through the life cycle of a building, because that will allow you to look at the CO2 uptake during that life cycle of a building. That's a first development. Second development, and that is a project again at the stage of research between Lafarge Holcim and Salidia. They have invented a non-hydraulic binder. Usually we use hydraulic binders, which means that our concrete has to be put in water to harden. Non-hydraulic binders means that the hardening process goes through the contact with air. And there again, contact with air means uptake of CO2 recarbonation during that process as well. That is a development because the non-hydraulic binder is used both in the cement manufacturing process, which means less limestone that we need, lower temperatures and therefore less CO2, probably 30% less CO2, but also in the concrete manufacturing, and that is exactly where the CO2 uptake is also taking place. So both areas of research currently ongoing, but yes, looking at recarbonation of CO2 in concrete.
Good. So rather well-prepared answer there. So the second question we have, I don't know, you see it probably. It's I think a little bit similar to the first one. So I'll move to the first question. And how about algae-based technologies to produce both fuels or specialty chemicals? So suppose this is for you, Johan.
When it comes to algae and the production of biofuels and large-scale bio-based chemicals, there is a fundamental problem. Now, why do people use microorganisms in industrial biotechnology? It's because you can put a lot of cells in a relatively small volume at a high density, providing a very high catalytic capacity, catalytic efficiency to convert substrate compounds into products. Algae need light. So when you make a high density culture of suspension of algae, the light cannot simply penetrate to the algae in the middle, and you can never reach any catalytic efficiency. So for the high scale production of biofuels and bio-based chemicals with a low value, the future of algae, I think, is very bleak, very weak. However, for the production of high-value compounds, of specialty compounds, like, let's say, polyunsaturated fatty acids, pharmaceutical compounds, or nutraceuticals, there algae can really have an important influence, because there you can work with low density cultures and where you can have actually the algae fed by the light. Another possibility has been used by a company in the United States is to use algae in the dark, just like you use yeast or use bacteria. And you use them, for instance, to convert sugar into oil, because they are very good in doing that, but not with light in the dark. And so when it comes to algae, the answer is very clear. For biofuels and low-value bio-based chemicals, I don't see a real future. But for specialty chemicals with a higher value, algae for sure have a future.
Thank you. And I also noticed in your presentation that the first pilot plant was in Europe, but the following 4 was in the Americas. So maybe one question to all panelists is really, are we too prudent when it comes to the environmental aspects in Europe and not enough focused on the sustainability of our jobs? Do our industries move out from Europe and actually pollute other places? Can I be that provocative? And then if I give the mic to Samir, look serious over there.
Thanks. I'll try to give less provocative answer to that. No, I don't think we should really move elsewhere. I think we are on the right track in addressing and we've done a lot in terms of addressing the sustainability and the CO2 and the capture and so on. I think we just have to make sure we get it right, and also make use of, if you take the steel industry, it's a very energy intensive sector. Why don't we look into reducing the intensiveness, but also capturing the heat and the CO2 and make value of that, rather than say, okay, no, we can't carry on like this. Let's move elsewhere. So yeah, that's my view.
Thank you very much. So let's see here what we have in form of questions. Is industrial symbiosis with process industries a way to foster a more circular economy? Wow. Yeah, give it a try.
I'll give it a try, but I think it comes back to what we said in the beginning. I mean, if you look at the steel sector, you're talking about scrap being used, which means scrap coming from cars that are scrapped, used in the electrical furnace. So basically you stay within the same industry. Huh? Whereas in our, I mean, and you also have contacts with other industries, as you said, you provide slag to the cement industry. The cement industry takes its raw materials, its energy for recovery from other industries. And I think that is why, yes, industrial symbiosis is, in my view, a key point for the circular economy. I mean, if we do not create that symbiosis between different industries, we will not have access to our raw materials, to our energy for recovery. So for me, both are interlinked and intricately part of the same picture, if I may say that for the panel, but I think that's what my answer would be.
Thank you. Might we also maybe have some comments on how the Internet of Things and information technologies will affect the basic industry? Maybe if I give it to...
Well, this is the information technology is continuously and extensively being embedded into industry now, and the trend I was told about is that it's about the fact that some information can be derived from materials being processed for the next steps of their processing. And this is information not available elsewhere. This is new trend, and it should help to find, or in other words, to tune the next processes to make them more efficient. And this is also the step towards the so famous Internet of Things, Internet or intranet of Things. Information processing, but the problem is that processing so big amount of information requires enormous amounts of capacity. So this is a necessity of employing clouds to process the large data. Simple example taken: a lot of diagnostic signals from every gearbox in hundreds of belt conveyors means millions of signals simultaneously being provided. No person can recognize them, but prepared algorithms and a cloud computing can do. So yes, industry is being enhanced with more information, but the problem is that only big companies can be able to make advantage of this because it requires quite substantial investments. Or collaboration. So both directions are good and are used.
Thank you. I think I can also complement your good answer there, because we have in our sector started to use CT scanning. So the thing when you go to hospital and you think you have a tumor or something, for logs in sawmills. And you know, the thing is, if you know how the log looks inside, you can saw it better. You save a few % of the raw material by this process. And that's a lot already. But actually, what does this few % mean for a sawmill? Well, okay, if you just count it like you make a material saving, you optimize the number of boards you get from a certain tree with a few %. That is still a lot of money. But if you think about an economy where you have a customer say, I want 50 cubic meters of a certain quality of timber. The sawmill today has to saw about 2,000 cubic meters. So about 10 times like that in order to get this final little part of material. Now, if they can know already from the beginning how to sort of, rotate the log before it goes into the sawmill, then they only have to cut 500 cubic meters to get those 200 in the end. So you have a factor 4 there. And this gives one example how measurement technology, how information technology can be used to really benefit the circular economy. Okay, we still have a few more minutes here, I think. But I just want to take the opportunity now. Is there anyone on the floor that feel you want to stand up and ask a question at this moment? No? Oh, maybe I didn't think so. It's not so. Then I will think we would take the final question, and maybe we make a short answer, all of us, and that would be, to what extent and in what time can scarce materials from outside EU be replaced by renewable resources or sources from inside EU? So what needs to be done for this? So maybe if meanwhile you're thinking I give a short answer, is that, well, when it comes to wood in Europe, we're actually very good at having a sustainable wood supply. Now the problem is a little bit that the Chinese start to buy the wood before we do something interesting from it. But to give one example of how much we can do is that one can make textiles from wood today. And if we make textiles from European trees, we could replace the whole world's cotton production at once, simply from Europe. So that's one example of what we can do. So with that, I'll leave it to you, Koen.
Well, I can be very brief because we have the two sources for us. I mean, limestone for us is not really an issue in terms of third countries because it's abundantly available in Europe. We have the quarries that are close to our cement plants, so limestone is available in Europe, is not an issue of a critical raw material in third countries. When it comes to fuels, that's what I discussed, primary fuels, petcoke, oil, we are replacing that with alternative fuels increasingly, but yeah, I mean, it is also available on world markets, but we try to diminish our CO2 footprint in that area.
Well, when it comes to my field, production of biofuels and bio-based chemicals, I think that the main challenges are technological. I mean, there was also a question about the reason why the second generation bioethanol production takes so long time to get into full scale in the market. I think that the main problem is not the policy, is the technological issue. And the plants, they cost about 150 million euro. And the investors, they also see, as you see, that the market penetration goes very slowly, and their conclusion is that process does not work very well. We need a better process, and they are waiting. That is why, of course, it's a circular system. They are waiting because the process does not work well, and when the process does not work well, actually there is not enough investment, not enough experience to make it better. So in my field, I think the main challenge is technologically.
One can remember that in fact people do not need raw materials at all, they need services. We want to speak to someone by telephone, but we don't need to have cable of copper between us. We can use cellular telephone. So as long as economy is ruling, better services using less raw material expand, and in fact our development still relies on decreasing the raw material impact on our life, on our service. So, and on the other hand, this is a difficult challenge for the mining industry, because mining industry produces something which is less and less costly in comparison to other things. It means it has to be more efficient. But, well, remember, services, not materials. Better services means less raw materials are used.
Thanks. Yeah, I mean, a couple of things really. I just want to go back to the point raised by Cohen about the, I think in this field, the circular economy, we need to look beyond our gates. And to be efficient, really, we need to work with other industries. I mean, like you mentioned, we've done it with the construction or with the auto. We need to be working with other industries. That's the best way, in my opinion, to get to an efficient point, because what is a waste in one place might be of value elsewhere, but also we can learn from one another. And I really encourage this. On the Internet of Things, for me, I think we see that as an opportunity, because once we have, especially in a large-scale industry like ours, once you dig deeper into what we do and how we do things, and once we have that understanding, it gives us a better opportunity to innovate and to improve. Of course, at this stage, we're trying to gather the data. But then once you have that data, you need to understand what can we do with it, and how we can make use of it in the best interest of the industry. And lastly, regarding the material, I have no doubt in my mind that we have to look for new materials. As we've been looking for Internet of Things or whatever, we need to explore what are the next generations. We've been doing things. If you take the steel industry again, we've been using the same ingredients, let's say, for centuries. I'm sure there are things out there that could make a difference. You gave the example of the textile. I'm sure there are a few bits and pieces there that we can make use. I mean, we are active in this area, exploring what are the next materials. Okay, we know now about graphene, but what's next? I mean, what are the next things that will come? That links me back to the first question. That's a circular, it's a loop. So if we start working collectively or breaking those barriers with other industries, we can find out. I mean, like in your case, you mentioned you can make a textile with wood. That's by branching to industries. Okay, thank you.
Okay, with that, I think that we will close this session. So thank you to the speakers. I'll give them an applause. And also thank you for myself. I will be moderating the biotech session tomorrow if you stay for the afternoon. So you might see each other then again. Okay, thank you very much. Bye-bye.